Okay. Yeah, can you see the slide?
Yes, sir.
Okay, can you read something from there?
Gauss law.
Yeah.
Gauss law.
Okay.
Displacement vector.
Right. Electric field vector.
Electric field, sir.
Yeah, right. Okay. Now, what does Gauss law say? It talks about what is the amount of charge enclosed by a closed surface. Okay, if Q is the amount of charge enclosed by a surface of area A, then Q by A gives you the displacement vector, or you just call it as epsilon naught E. Okay, you call it as epsilon naught E. Okay, or okay, in Gauss law you'll say that integral uh, what do you say, E dot ds, okay, is equal to q by epsilon naught. Integral E dot ds is equal to q by epsilon naught. Okay, that's what you say, right? I don't know whether you remember or not. Okay, so anyway, Gauss law says that okay, charge density is nothing but okay, q by a, and that is nothing but your displacement vector. Okay, keep that as well. I mean, I'll explain it later. Now come to this place. Okay, I have a metal plate. Blue one is a metal plate, and I place some charges on it. Okay, what is the total amount of charge I placed? Capital Q. Capital Q is the amount of charge placed on this one. And I'll assume that this has got area A. This has got area A. So I have placed capital Q charge on area A. So the charge density will be rho, which is equal to Q by A. The charge density is rho, which is equal to Q by A. Okay, and then on the opposite plate I have negative charges, which is again minus q, and because it's also of area A, okay, the charge density here is minus q by A. Okay, anyway, between these two metal plates, or to say between these two charges, there will be a electric field. Okay, electric field exists everywhere whenever you have a charge. Okay, so electric field exists around the charged particle. Okay, you have charged particles, so you'll have electric field. If you have okay, magnetic particles, you'll have magnetic field. If you have mass, you'll have gravitational field. Okay, now okay, ikkada I just wanted to tell something else. Okay, 1 second. Yeah, how do you know that the electric field exists or not? Okay, for example, okay, all of you independently you can think. Okay, now if you just extend your hand towards your right, okay, can you tell me, okay, at the tip of your hand, do you have electric field over there or not? 5, 4, 3, 2, 1. Can you?
No, sir.
Now, how to know? Okay, how do you know whether the electric field exists or not? 5, 4, 3, 2, 1. Okay, I'll change the question. Okay, now you extend your right hand, and at the tip of it, can you say that there is gravity over there? 5, 4, 3,
Yes, sir.
2. Okay, who said
Yes,
yes?
Yes,
sir.
Oh, many
me.
many answers are coming
Me.
with yes. Okay. Now, how do you know that the gravity exists?
Because the hand is not floating.
Okay. Okay. I mean, when I stretch my hand, it will be there. I mean, it will be. I mean, in the same position for some time, right? So you mean to say that gravity does not exist? I'm saying at the tip of my hand. Okay, right? At after my okay, let me say fingertip. Okay. So do I have okay gravity at that point? 5, 4. Answer. Your answers are right every time. Okay. Let me tell
Yes,
you.
yes, sir.
Yes,
Yes,
Yes.
right,
sir.
right. How do you prove that the gravity exists over there? 5, 4.
At the tip of my hand place, we need to drop an object.
Okay, good. You place an object at the tip of my hand and it will fall. Okay, if it falls, gravity exists. If it does not fall, gravity does not exist. Avuna
Gravity does
kada?
not.
Right?
Yes, sir.
Okay, then what shall I do? I'll place a photon. Let me say I'll shoot a photon through my tip of my hand. I'll shoot a photon through the tip of my hand. Okay, like this. Will the photon fall? 5, 4, 3, 2, 1. Will the photon fall? 5, 4, 3, 2, 1.
No, sir.
Why?
It's a particle, so it moves randomly. Or in
No, no,
a
no, 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 no. It's not. Okay, that's not the argument. Answer is right, but argument is wrong. Yeah. Photon does not fall. Yeah. Why? 5, 4, 3, 2,
It
1.
doesn't have charge.
No. Argument is wrong. 5, 4, 3, 2, 1. What? What do you require to experience gravity? 5, 4.
sir, it
Weight.
doesn't have mass.
Weight, sir.
Mass.
Right. Oh,
Mass.
don't use weight. Don't
Weight.
use the word weight.
Mass.
Don't use the word weight. Okay. Weight is a force. Okay.
Mass.
Okay. It does not experience weight because there is no mass to it. Because there is no mass to it. Okay. So if you want to experience gravity, you require something which has got mass. Okay. How do you? Okay. I mean, how is gravitational field generated? Because of other mass. Okay, because of other mass. So if you don't have the first mass, there is no gravitational field. When there is no gravitational field, you cannot say whether whether something else has got gravity or not, or whether something else has mass or not. Okay, you can say whether something has got mass or not only when you have something else, okay, which has mass and is generating gravitational field. Okay, I don't know whether I'm making some sense or not. Okay, I'll take the example again. Okay, the simple question is, okay, as I said, okay, if I take my pen and I want to say whether this has got charge or not, then what shall I do? If I say that, okay, I'll take my pen and ask you, okay, whether this has got charge or not, what will you do?
Place it in an electric field, sir.
Beautiful, beautiful. Okay, that's it. Now place it in an electric field. If it gets affected by the electric field, that implies this also has got charge. If it does not get affected by the electric field, that implies it does not have charge. Simple. Exactly same argument is placed for gravity. Exactly same argument is placed for magnetic field and magnetic particles also. Okay, and the beauty is that, okay, you can exactly place this argument even when somebody asks you whether God exists or not. Okay, you can only if you have that kind of what do you say, interactive ability, you will know whether the other person exists or the other field exists or not. For me, God is nothing but a field. Okay, and if I want to experience that field, I need to have a part of it in me. That's it. Okay, that's okay. Okay, forget about the last one. Okay, that is only to I'm going to say generalize it. But important point is, you can detect a magnetic field only when you have a magnetic particle. You can detect an electric field only when you have an electrical particle, and you can detect a gravitational field only you have a gravitational particle, that is mass particle. Okay, right. Now coming to this case, okay, I placed some charges on this one. Okay, okay, capital Q charge is placed, and so I'm calling it as rho, the charge density. Rho, the charge density. What is this rho? Okay, rho charge density, applied charge density. That implies I'm applying this plus Q charge on this plate. Because I'm applying this, I call it as applied charge, and this is applied charge density. This is applied charge density. That's my way of looking at it. Okay. Now, in this case, I have applied charges, and these applied charges are generating electric lines of force. And these electric lines of force are uniform. These electric lines of force are uniform. Okay, right? Now, in this parallel plate arrangement, I place a dielectric material. I place a dielectric material. Okay. when I place a dielectric material, okay, okay, now this one is your dielectric material. Okay, now the extreme right one is dielectric material, and this one is your parallel plate capacitor. Okay, now is the dielectric, okay, as you see here, is the dielectric charged? Is it charged now? 5,
No, sir.
4.
No.
It does not have any charges. It is a neutral material,
No, sir.
right? It's a neutral material. Now what am I doing? I'm taking this dielectric material and placing it in the parallel plate capacitor combination. So, okay, parallel plate combination. Okay, I'll not call it as capacitor right now. Okay, so I'll take this dielectric and place it into the parallel plate combination. When I place this dielectric in the parallel plate combination, what's happening? What's happening here?
Polarization.
Beautiful. Yeah, it is getting polarized. Okay, why are you saying that it is getting polarized?
One type of charge is going to the another side.
Okay, right. Okay, so from this neutral material, okay, okay, one kind of charges are moving to one side and another kind of charges are moving to another side. What do the red arrows represent here? 5 seconds. 5, 4, 3, 2, 1. What do the red arrows represent? 5 seconds. 5,
Polarization vectors.
4, no, 3, 2, 1. What do the red lines represent, arrows represent here? Simple, okay? 5,
Polarization.
4, 3, 2, 1. Oh,
Direction of charge.
no. Okay, what do the blue
Direction
arrows
of
represent here?
current.
No. What do the blue arrows represent here? What do the blue arrows represent here? 5.
Electric field.
Electric field lines. Electric field lines. Yes or no? When do you get electric field lines? Whenever you have positive charges and negative charges separated by some distance. Now why, okay, why do you have this red, red lines now? What do the red lines represent?
Polarized field lines.
Right, good. Okay, electric field lines generated because of polarization. Excellent. Okay, these red lines are the electric lines of electric field lines produced because of polarization. Okay, in this unpolarized material, you don't have these lines of force. Okay, in this unpolarized material, you don't have lines of force. Okay, right.